Hello everyone. This is the second session in a series of presentations on measurements in epidemiology. We will be talking about tools of measurement as continuing from the concept of variables. Imagine variables. There are nominal variables, there are ordinal variables, there are continuous variables. And the primitive variable which we'll be talking about today and the derivations thereof is actually something of a nominal character. The simplest nominal variable will be which takes on two values. For example, whether you are a statistician or a psychometrician, or whether you are a male or a female, whether you are uh, answering a question correctly or not, if something is present or absent. So, in other words, some binary variables can also be called as dichotomous variable, in that it takes only two values. So this is the simplest variable which you can think of. There are only two levels. And the binary variables are peculiar in that you can actually take any continuous variables, provide a cutoff, and then group them into two. Like for example, age, which is actually a continuous variable. You can make it into a binary or a dichotomous variables by providing a cutoff like less than 35 and 35 or more. So that way you can make a continuous variable into a simple nominal binary or dichotomous variable. Binary and dichotomous means the same, but it matters whether you're a statistician who will say that it's a binary variable, and if you're a psychometrician, you will call it a dichotomous variable. It matters to that extent only. And from this variable in your data set, what you can do is you can create ratios. What are ratios? Ratios is the first tool of measurement what we're going to talk about. It expresses a relation in size between two random quantities. Random in a sense, they take on two values like in a binary or dichotomous variable like male to that of females. Males don't include females and females don't include males, or whether the question gets an answer which can be classified as true or false. The true to false becomes a ratio. True is to false, and or something is present or absent, then the ratio becomes yes to no. So the examples are something like sex ratio, doctor population ratio, and then child woman ratio. Typically speaking, the ratios have two pieces, just like something which we're going to talk about in future. Numerator, which is actually x, and denominator y, even though typically it's not a denominator, but the way you put it up is something like x is to y, or even you can say x to x by divided by y, but it's not exactly division, it's x by y, and x is not part of y and y is not part of x, so that means that these are mutually exclusive. To make the situation more clearer, something of variable which is connected to you, see, look at the cells in the blood. The ratio of white blood cells to that of the red cells. White blood cells are not red cells, and red cells are not white blood cells. So that means that the 1 is to 600 or 1 by 600 is actually a ratio of white blood cell to red cell, and it has a meaning in your science as well. And each white cell represents around 600 red cells. So this is a typical ratio what you're going to talk about. And the numerator and denominator may also involve an interval of time or maybe instantaneous in time. For example, the number of children with scabies at a certain time and the number of children with malnutrition at a certain time. In this case, actually, these are two random quantities. So you can make anything to everything else as a ratio with the condition that the denominator is not including in its fold the numerator. So I think the concept is pretty clear. So you can create ratios, you can express the ratios. Only thing is, in that one example which I gave, doctor population ratio, doctors are part of the population, but when you generally talk about it, the number of doctors is very less. So the distinction doesn't exactly matter very much. Moving on, the next kind of tool of measurement what we're going to use is proportions. And a proportion, oh, by the way, proportion is another kind of a ratio, but it's not a ratio, it's a proportion. This indicates a relation of a part in terms of magnitude to the whole. So that means that the part is part of the whole. The number of children with scabies at a certain time, at a point of time, into 100 to make it into a non-decimal number or an integer, the total number of children in the village at the same time. That means that the proportion of children affected with scabies at a particular point of time in a village. This is something which you have heard about probably in terms of prevalence. At the same time, in a continuum of time, you are telling a cross-sectional nature of the population, a prevalence, a condition which is actually present in a population at a particular point of time, and that is expressed as a proportion, and wherein the numerator is part of denominator. And the numerator, starting from the binary variable or a dichotomous variable, these are the number of yeses out of the total population, at risk of that particular situation, or the number of true answers out of the whole classroom full of students, or the condition which is present in a group of people in terms of presence of scabies and absence of scabies. Only thing is present divided by present plus absent, and that actually can be created from a dichotomous variable or a binary variable. So in a data set, if you have a binary variable or a dichotomous variable, the things which you can create is one, a ratio, and second, a proportion. And the ratio, I already given examples, and a proportion, the best example will be something like a point prevalence of a condition. I'm making it as a definite emphasis that I'm using point prevalence of a condition in a given point in time, the number of people with a certain a characteristic out of the total population. So that's the typical thing about proportion. Only thing is we would like to call some proportion prevalence if we are dealing with a real community, not a thing like hospital population, even though you might be tempted to use hospital prevalence as an outcome at some point of time in your research presentations. Now we're going to talk about a little bit more in detail about numerators and denominator. What is the numerator? N divided by D, as I call it. Many times the data for calculations actually the numerator and the denominator may not be very easily available in a data set. Like the data set is humongous. It's a whole population. You may not be able to get binary variables from a huge population. For example, I'll be giving more detailed examples later on. This data might come from different sources. Like numerator I'll pick from one point, and then the denominator I'll pick from another point and put it together and create a new proportion, as you call it, if you want to call it. So what I'll do is, for example, something known as a period prevalence of a disease. If you have a primary health center and you have a population of 30,000, and there are people who are reporting with a certain condition over the year, what I do is I take the number of reported cases in that year, typically speaking, a single instance per individual out of the whole population. How many people reported with the condition in that year? Then what I do is, I know the population of a PHC is 30,000 population. I just make a proportion out of that. And that actually is the other side of prevalence, which I call it period prevalence, because it's not a point in time, it's actually a duration in time, so it becomes period prevalence of a disease. So numerators and denominators might come from different directions, and if I don't have a clue about what the population is exactly, say in the terms of country or a state or something, I know the population at the time of census. I know probably the January population is not as equal to the December population is. So what I do is I'll take what is known as a mid-year population by extrapolating it from the census population and adding the number of years to the period which I'm considering. Then that mid-year population becomes the at-risk population on which I'll be calculating the period prevalence. So now you get the point, So it may not be like, just going through an SPSS set of data and then creating a ratio or a proportion and putting it out as a point prevalence. No, it's not that simple. In real life, health department will be using these kind of different numerators and denominators from different places and putting hashing it up to form things like period prevalence, which is almost, if you look at it very carefully, and it's almost like the calculation of incidence, which I'll come to in a moment. The denominator, as in this particular case, was the MYP, or the media population, and I already told you how to calculate it, and the population keeps on changing in this particular situation. Otherwise, I'll just take a fixed set of number as a population and then I calculate it. So the equation goes like reported cases old and new of a specified disease during a given period of time interval into 100 divided by estimated media population at risk. And the typical multiplier here is something like 100, because old and new together probably will have a decent numerator, so that you don't have to really struggle to make a non-decimal number in the end. So prevalence usually goes by percentage, just like proportion. Whereas the next thing what we want to talk about probably might not be the same thing. Herein we are moving to the concept of rates. Rates has got something which the ratios don't have, and of course, proportions don't have something which the ratios lack in, and then rates have something additional to both ratios as proportions lack in. Here, a rate actually measures the occurrence of a particular event. It's actually development. It's a dynamic thing. It's not just over a period of time or at a point of time. It's actually happening over a given time period from January to December. The disease keeps on developing anew, and the cases become reported, or deaths occur. So this is actually a dynamic process, for which what we do is we calculate what is known as a rate. A rate comprises of three elements. One is the already discussed numerator, which might come from one source, just like we mentioned, may not be from a data set purely. And then you take a denominator, typically like media population, and then add a time specification to the whole thing, and you have a multiplier just like a proportion. You will ask me what is actually the difference between the two. Here actually we are actually looking at not prevalence. We are moving on to the next concept, that is incidence, the rate at which a new disease develops in a population over a period of time. And that actually indicates a change in an event which takes place continuously in a population over a period of time. And that actually is a statement of risk of developing a condition in a population given a average individual. Moving on, rates are not proportions. Rates are actually not ratios like an odds of developing having an exposure in a disease condition. It's not a proportion, it's actually a probability. Like we say that, okay, there were 500 deaths from motor vehicle accidents in city A during 2010. We are just telling the number of deaths in that population, nothing much. You're not even calculating a ratio, you're not even calculating the proportion. To be meaningful, what I have to do is that how that 500 deaths evolved. Okay, if a person were to travel so many kilometers in a year, what is his chance of actually meeting with a tragic end? So here, we are moving forward as a rate. It's not just media population. We are talking about a dynamic state of events wherein people are traveling all the time, and then over a period of time, for a person, what is the risk of him meeting with a bad turn of events? Person distance, for example, passenger miles. And then the utility is like, you can calculate the passenger mile incidence of deaths in city A, and you can calculate the same thing with city B, and you can compare between the two things. Crude proportion or a ratio may not be very relevant in this particular situation. So an incidence becoming what is known as an incident density becomes more meaningful in this particular situation. Amplifying that, I can say that the number of accidents per thousand vehicles or per million vehicle miles will also be a more useful denominator than the total population. Many of them In fact, they may not be using vehicles. So, the people who are not using vehicle, they will have less amount of vehicle miles, and they'll definitely have less number of vehicles also. So we are actually more accurate in terms of telling what happened to people who are exposed to that danger, rather than just taking a media population and saying, okay, on an average, this was the risk of them meeting with a particularly bad turn of event. And rates are actually multiplied. The multiplier used in rates will be more than 100 usually, because it will be a, a, a rare kind of event, or rarer kind of event compared to prevalence numbers, because they don't add up the old cases. So that means the number will be less, and occurrence of that condition will be much less in a population in a given year and all that. So we can start anywhere from multiplying with 1,000, and when the number of events become less, you can actually escalate it to 10,000, 100,000, a million, just like in the case of acute flaccid paralysis nowadays, with the polio being eradicated. So that is actually done to avoid fractions which are a little bit difficult for typical medical professionals to understand. And that's thank you from my end.